12th lecture, and we have our problem session 3. The first problem that we are going to discuss is 7.2, and the problem is this: the circuit consists of a switch which has two positions, and it is thrown from position 1 to position 2 at t equal to 0. There is a battery of voltage V, and the switch has an inductance L, a capacitance C, and a resistance R. The response is the voltage across this V0t, and to terminal 2 is connected another source V sub g of t plus minus at t equal to 0. T equal to 0 minus, the switch is in position 1, and after having been at 1 for a long time, it is switched off to position 2. The source voltage is VGT equal to V1 e to the minus alpha t sine of beta t. Source voltage is this. What you are required to find out is the transform of V0t, that is V0s. Then find the initial and final values, that is V0 0 plus and V0 infinity. These are another two quantities to be found out, and then part C is sketch one possible set of locations for the critical frequencies in the S plane and write the form of the response V0t. Only the form is required, and under bracket it says do not take the inverse transform, okay? Just the form of the response that is needed. Now looking at this circuit, you notice that since this switch was in position 1 for a long time, if we indicate this current as IL, and then IL of 0 minus is, by inspection, it is V by R, because capacitor acts as open, L acts as short, and therefore IL of 0 minus is equal to V by R, and the other quantity is the energy storage element is capacitance C, and obviously at 0 minus C shall be charged to the voltage V, and therefore V0 0 minus, V0 is the voltage across capacitor, so V0 0 minus is equal to capital V. These are the conditions at t equal to 0 minus. Now if I draw the transformed equivalent circuit for t greater than equal to 0 plus, then V sub g of s and the transform of the given function V1 e to the minus alpha t sine of beta t would be V1 beta divided by s plus alpha whole squared plus beta squared. We know this transform, e to the minus alpha t sine of beta t and with this polarity. Then we have the inductor L, which has an initial current, and therefore it is the inductor L without an initial current plus a voltage source. We are not using a current source for obvious reasons, okay? Yes, this will be minus plus, and it would be L IL of 0 minus, so it is VL by R. This is the voltage source, okay? Then the capacitor C can be looked upon as an initially uncharged capacitor in series with a voltage source whose value is, but I am talking of the in transform domain, so it will be V by S. Is that okay? The transform domain. and then I have the resistance R and V0t. You must, yes, V0s, that is correct, because I am talking of the transform domain quantity. The thing that you should notice here is that I am not solving this problem by transfer function approach. I am not writing the transfer function at all, because there are initial conditions, and if there are initial conditions in the network, the transfer function is not defined. Agreed? You can define a transfer function now, you can define V0 by Vg or any other network, but I could not do it right from the circuit. I could not write in terms of impedances, admittances and inspection, because there are initial conditions. Okay. You can now define a transfer function with those initial conditions. Okay. Now, if you look at this circuit, what what approach should you follow to derive the value of V0? Pardon me? Thevenin's theorem. Thevenin's theorem will require finding out an open circuit voltage here and the impedance looking back and so on. That is a simpler way. Just node equation, just one node equation. This node whose value is V0, and you see you sum up the currents, this current plus this current plus this current, sum up them to be equal to 0. And if I write systematically, it would be V0 minus V1 beta divided by S plus alpha whole squared plus beta squared minus VL by R. Is that clear? There are two sources. So, V0 minus this source, that will be the drop in L. So, you divide by SL, that will give the current in the inductor, plus V0 minus V by S divided by 1 over SC, okay, divided by the impedance, that will be the current through the capacitor. Current through the capacitor will be V0 minus this voltage divided by the impedance plus V0 by R would be equal to 0. Now, I have done the simplification. Requires a bit of algebra. Keep the V0 terms on the left hand side, you get 1 over SL plus SC plus 1 over R. This would be equal to transfer everything else to the right hand side and simplify. This simplification algebra, I shall leave it to you. My final result after simplification, you must take all my results with a pinch of salt. Okay, you must verify, because I make many mistakes. I have made many mistakes in life. I shall continue to do so, and that's how I shall prove that I am a human being. Okay, my final result comes like this. No, let me give you the further simplified expression. I omit all these steps and I simply write V0 equal to 1 over LC. This is what I get: V1 beta plus VL by R 1 plus SCR multiplied by S plus alpha whole squared plus beta squared divided by S squared plus S 1 by CR plus 1 over LC. You see how I have put this, the leading coefficient I have made equal to unity, multiplied by S plus alpha whole squared plus beta squared. I am not claiming accuracy of this, it may be right, it may not be right, but this is what I get. Okay. If you get anything else than this, please do point out to me. Okay. Please do tell me. Now, this is obviously a rational function. I put it in the form of a rational function. So, this is n of s by d of s, and it is equal to the network function, not network function, it is V0 of s. It is not a network function, it is a voltage transfer.
How do we get VL by R?
How do I get VL by R? This is by simplification.
This So show me your SVL by R.
No, that S comes here, SCR. Since you have raised the question, oh, I have multiplied by SL. You see, what I get is, let me this VL by R. This VL by R is already here, divided by SL. Then I have multiplied by SL both sides. You see, that is how I get S squared LC plus SL by R and so on and so forth. If it is wrong, let me know later. Dimensionally, it is correct. Okay, that I have checked. Now, therefore, the next question is part B says find out V0 of 0 plus. Now, I could do this from the physical considerations. Physical considerations, there is no impulses in the circuit and therefore the voltage across the capacitor must be continuous. So, V0 0 plus should be equal to V. But it is instructive to find out from this function V0 of S, if the transform is given by the initial value theorem. Initial value theorem says that if the degree of the numerator is less than the degree of the denominator, okay, initial value theorem says that V0 0 plus should be equal to limit S tend to infinity S times V0 S. All right, this is the initial value theorem. And now, if you multiply this by S,
so this initial value theorem is only if the degree of the numerator is less than the degree of the
that's correct. That means in the response of the circuit there should be no delta function. Agreed? Now, if you multiply this by S and take lead S to go, allow S to go to infinity, obviously only the highest power terms shall be of any interest. Let us see what are these highest power terms. You see, this would be S squared, this gives an S, so it will be S cubed, and you are multiplying by S, so it is S to the fourth. So, what I shall have is VL by R, this VL by R multiplied by SCR, I ignore the 1 because I am only concerned with the highest power term, multiplied by S squared from here, divided by what is the highest power term here, S to the fourth, S squared and S squared.
Yes.
So and
another S in the numerator because we are multiplying by S.
That is correct. That is correct. And this obviously is equal to, how come?
So we left 1 by
Ah, we made a mistake. We left this 1 by LC. So this must come here, and therefore this is equal to V. It cannot be otherwise. No voltage can be the product of V and LC. Dimensionally incorrect, so it should immediately point out that we left out here. Now, if I want to find out V0 of infinity, then the final value theorem says that final value theorem is valid under a certain constraint. What is the constraint? You have done Laplace transform in signals in system. What is the constraint on the final value theorem? No poles in the right half plane. No poles in right half plane. If there are poles in the right half plane, then what happens? The system is unstable, so it breaks into oscillation. Amplitude can go to infinity. Obviously, we cannot apply any logical procedure to find the value at infinity for an unstable system. Okay. So, poles in right half plane, is there guaranteed? Yes, it is guaranteed because 1 by CR is a positive quantity, 1 by LC is a positive quantity. So, the roots of this shall lie in the left half plane, minus 1 by CR plus minus etc., etc. And by definition the source that is given alpha and beta we assume positive, and therefore these poles are also in the left half plane. Okay. If poles are in left half plane, then V0 of infinity would be limit S tends to 0 S V0 of S. S tends to 0 S V0 of S, alright. And you see S tends to 0 only the lowest power terms dominate. So, 1 by LC and beta squared in the denominator, and in the numerator it would be V1 beta plus VL by R multiplied by alpha squared plus beta squared. But why am I doing all this? There is a multiplication by S, and when S tends to 0, whatever the other quantity is, unless it is infinite, it is a big 0. And this also is it tallies with the physical concepts. The source itself is an exponentially decaying source, e to the minus alpha t sine of beta t, and therefore, after infinite amount of time the capacitor will discharge completely. There will be no source for charging, and therefore, the voltage shall be 0. Is that okay?
Can we directly say that when we solve for it, we see that the power of S and numerator and denominator are same. So can we directly say this?
Power of S in numerator and denominator are not the same. This is 3 and this is 4.
So when we multiply it by S,
When you multiply by S, the power of S shall determine the behavior at infinity, not at 0. At 0 it is the lowest power term, and the lowest power term, when we multiply this by S, the lowest power term obviously contains an S, and therefore when S goes to 0, it is 0. This should be, it should be possible to say this by inspection of this. This is a cubic polynomial. When we multiply by S, it becomes a 4th degree polynomial with the lowest power term equal to some constant multiplied by S. In the denominator, it is also a 4th degree polynomial. The constant term is 1 by LC multiplied by alpha square plus beta square, and therefore when S goes to 0, the numerator goes to 0, denominator remains a constant, and the whole thing goes to 0. It must tally whatever the complexity of the mathematical expression, the final result must tally with common sense. If it does not, then you better look into your mathematics. It is mathematics which can go wrong, common sense often goes wrong, but not for an expert engineer. The last part of the question is, let me write this down once again. V0 of S equal to 1 by LC times a cubic polynomial divided by S squared plus S by CR plus 1 over LC times S plus alpha whole squared plus beta squared. And in the numerator you have a cubic polynomial. Okay, let us write this as n of S. I do not want to write this expression again, okay, because part C says do not invert. You just give me the form of the, choose a location, a possible location of the poles, and then give me the form of the voltage response in the time domain. Okay. Now, possible location, these these represent poles of the excitation, and these are the natural, these represent the natural frequencies of the network. Now, depending on the values of R, L and C, the poles can be on the negative real axis, or can be coincident on the negative real axis, or can be complex. Let us say they are complex. A perfectly possible location.
Sir,
Yes.
so which are the poles of excitation?
These are minus alpha plus minus j beta. These come from the excitation function. That one part comes from H of S, the other part comes from E of S. That is network function multiplied by excitation transform. Now, obviously these are, let us say, if this is j beta and this point is minus alpha, then these two poles come from the excitation function. These generate two more poles which can be real, which can be complex. Okay. Suppose they are complex. A perfectly possible location would be like this, let us say these poles are here. They must be complex conjugates. And suppose, use another color. Suppose this is j beta prime and this point is minus alpha prime. This is a perfectly legitimate location of the poles. There are 4 poles. Are there any more? No, because n of S is of degree 3. if the degree was 5, let us say, then there would have been a pole at infinity. Okay. It is of degree 3. So, these are the only locations of poles, and I can now write down n of V0 of s. After choosing this, I can write down some let us say n1 of s, some polynomial in the numerator which is of degree 3, which is simply 1 by LC multiplied by n of s divided by s plus alpha whole squared plus beta squared. This is one set of poles, and the other is s plus alpha prime whole squared plus beta prime squared. Okay. Now, if I make a partial fraction expansion and take the inverse transform, does it stand to reason that V0 t will be of the form k1 e to the minus alpha t sine of beta t plus theta, okay, due to these two poles, and the other term would be k2 e to the minus alpha prime t sine of beta prime t plus theta prime.
So, but won't looking at the expression of denominators, sir, we find that there are 4 poles.
That is right. There are 4 poles.
But in the numerator there are.
Numerator can even be constant. It does not matter.
Excuse me, sir.
Yeah.
Sir, if there is a cancellation of denominator over by numerator,
If there are cancellations, then you have to cancel them.
then we'll have to see the numerator also. Sir.
We have to see, yes. Yes, in this case, the possibility of cancellation does not arise, because we are given these symbols only. If the numerical values are given, possibly they could. Yes, that is a good question. We assume here that the values are such that there are no cancellations. Okay. If there are no cancellations, then this will be the form. There are 4 poles. Accordingly, there are 4 constants to be determined: k1 theta, k2 theta prime. You have to use 4 conditions to determine this, and you know 2 of them, I0 plus and V. No, you know V0 plus, V0 0 plus, V0 infinity. You will have to possibly find out the primes also. Okay. But if you are working in the frequency domain, you do not do anything like that. You simply expand into partial fraction and get the result. Now, in expanding into partial fraction, tricks of the trade, one trick of the trade is, do not expand in terms of the complex poles. You can say, I will say A1 divided by S plus alpha plus j beta, and the other is A2 divided by S plus alpha minus j beta. You can do that, S plus alpha minus j beta. You can do that, and then find A1, A2, A3, A4. If you do that by mistake, even then there is a saving grace, that because the sum of the two has to give you a real rational function, A2 must be A1 star. This simplifies things, but do not do that. This is a wrong route, and you are trying to save the save time. Saving time is possible if you look at this and the degree of the numerator is 1 less, it is less than the denominator, so there are no poles at infinity. Then you simply write this in the following form. You write this as sum A s plus b divided by s plus alpha whole squared plus beta squared plus c s plus d, sum c s plus d s plus alpha prime squared plus beta prime squared. How do I know that this will take care of the numerator? The numerator is of degree 3. If you clear this out, obviously the numerator will be of degree 3. There are 4 constants here, A, B, C and D. You find out the constants. Okay? And then invert term by term. You see, if you have a term like this, then obviously it can be expressed, the inverse transform will be sum of a cosine and a sine, which can be combined into a single sine. Agree? So this would be a shorter route to success. Alright? You can have a wrong route to failure. If you follow a wrong route, the most possible expectation is a failure. Okay, now let us go to the next problem. Next problem would be 7.4. And the problem is the following.
So in this problem you also to calculate the constant.
You shall have to, otherwise, no. Since you are required to find out only the form, constants are not required. I chose these complex locations to be able to write a very simple form. Okay. Now, in the question doesn't ask to find the constants. It's your choice now. If you want to waste time without any reward, you are most welcome to do it, but don't do it. My advice is don't do it. Okay. 7.4. There is a circuit E of t 1 ohm and half farad. This is the circuit. The voltage source E of t has the following waveform. This is to be seen carefully. It rises linearly to a value of 1 at t equal to 1, then it falls at t equal to 1, it falls to minus 1, then it rises linearly again to 0 at t equal to 2, and then remains 0 throughout. Okay, this is the plot of E t versus t. Obviously, what you have to find out is the response I of t, assuming 0 initial conditions. You have to find out I of t. Obviously, all that you have to find out is the transform of this waveform. Then the current transform would be the voltage transform divided by the impedance, which is R plus 1 over SC. I can do this because there are no initial conditions. Otherwise, I would have to write in terms of initial condition, then apply whatever I wish to apply. Okay. Now, obviously, the first thing to do is to express E of t in terms of the known functions, step, impulse, and so on. And my solution for E of t is that I take t of E of t. There is a systematic way of deriving such functions. You see, if I take t of E of t, that is unit ramp, what will it do? It goes like this. Now, what I want to do is at t equal to 1, I want to bring down by 2 units. So, I subtract 2 u of t minus 1. It must occur only at t equal to 1. So, I subtract 2 u of t minus 1, then I shall get this. Then at t equal to 2, I want to kill the ramp, and therefore I subtract minus 2 t minus 2 u of t minus 2. Agreed? You can do this by inspection. No t. Second term is only to bring this ramp down by 2 units to minus 1. Then it goes like this, then I kill this. Okay. You must be very careful about writing this by observation. T minus 2 is sufficient. Yes, I was wondering why it is taking so much time to point out the mistake. All right. These are the types of mistakes one does by observation. Okay. So, what is E of s? I can write also this by observation, 1 by s squared minus 2 e to the minus s, all right, minus what? 1 by s squared e to the minus 2s. So, this is my excitation waveform, all right. Yeah.
The second term won't have an s in
Second term won't have
s in denominator. So in the transition.
Yes, of course it shall. Very good. Any other mistake? No. All right. So, my E of s, I reproduce this here, 1 by s squared 1 minus e to the minus 2s. I combine the first and the third term, minus 2 e to the minus s divided by s. Okay. and therefore, the current transform would be E of S divided by 1 plus 1 by S C, that would be 2 divided by S. Agreed? This is the impedance, 1 ohm and half farad capacitor. So, this is equal to S E of S divided by S plus 2. Therefore, this is equal to 1 minus e to the minus 2s. If you substitute now, this is divided by s squared multiplied by s squared, so it will be s times s plus 2 minus this s and s will cancel. So, I will get 2 divided by s plus 2 e to the minus s. Is that correct?
Yes, yes.
Oh, wonderful. So, I can write this as 1 by s minus 1 over s plus 2 multiplied by half multiplied by 1 minus e to the minus 2s. See, everything by inspection, minus 2 divided by s plus 2 e to the minus s, and the transform, inverse transform, can now be written down term by term. You see, I of t will be equal to half 1 minus e to the minus 2t ut. This takes care of this factor. Then I multiply by e to the minus 2s. So, t will be replaced by t minus 2. That would be minus half 1 minus e to the minus 2 t minus 2 multiplied by u of t minus 2. Then minus this term would be twice, yes, e to the minus 2, then no, t minus 1, okay, t minus 1 because of the e to the minus s, and then we must not forget u of t minus 1. You see, a complete response has been obtained. There are many places, many ups and downs, and one can make a mistake very, very easily. Doing a mistake, committing a mistake is absolutely no problem. Doing it correctly is a problem. Our next problem would be 7.6. 7.6 concerns this circuit. A switch S which is opened at t equal to 0. Oh, I see. Opened at t equal to 0, and there is a current source here, I of t. If it is closed, then the current flows like this. After opening, the current flows in the main circuit, and the main circuit is, well, for, you can say, personal bias, I do not like capital X to be used for a resistance. Capital X is reserved for reactance. So, I will use capital R, all right. Capital R, then you have a circuit 1 Henry and half farad. The response required is V of t, not required. Look at the condition of the problem. This circuit has 0 initial energy. Okay. In other words, IL 0 minus is 0, Vc 0 minus is 0. Okay. Initial energy is 0. At t equal to 0, the switch S is opened. Find the value of the resistor R. You are required to find out R such that the response is Vt equal to 0.5 sine of root 2 t ut. The response is this: if the excitation is t e to the minus root 2 t ut. Okay, this is the condition. It is this, Vt is found to be this, find out R. All right. So, all you have to do is to multiply the current transform by the impedance and equate that to the transform of the voltage. Let us find out this a bit carefully. I of t equal to t e to the minus root 2 t. So, what is capital I of s?
1 by s plus root 2 whole
1 by s plus root 2 whole
square.
square, that is absolutely correct. Does this require consulting a table? No, you should remember this. Well, to recall briefly, e to the minus root 2 t, the transform is 1 by s plus root 2, and if you multiply this by t and had a negative sign, then this would be differentiation of this, which is equal to minus 1 over s plus root 2 whole square, and therefore the transform of t to the minus root 2 t. I have made a mistake, this must be multiplied by ut. Okay. And the voltage transform V of s is 0.5, the transform of sin omega t is simply omega divided by s squared plus omega squared, which is 2. Agreed? So, this is equal to current transform, which is 1 over s plus root 2 whole square, this is the current transform, multiplied by the impedance, which is R, plus the impedance of a capacitor and an inductor in parallel is SL divided by s squared LC plus 1. So, L is 1, so s divided by s squared LC, this will be s squared by 2 plus 1. All right. So, all that you have to do now is to find out R such that these two sides are equal. Agreed? Now, the things have been so chosen that capital R comes out as a constant independent of s. If you do it wrongly, then you can be assured that R will come out as a function of s, and then you know immediately that you have made a mistake. My solution is R equal to 1 by root 2. Well, obviously it is not very difficult, because s square by 2, s square plus 2 will come, this will cancel, and so on and so forth. That algebra you can do. My next problem would be 7.6. Pardon me? Oh, 7.6 I have done, so 7.8. Haven't I done 7.8? I have done that in the class. So, I go to 7.9. 7.9 would turn out to be interesting. For the transformer shown, the transformer is this, the switch S is turned on at t equal to 0. There is a 3 ohm resistor, and then there is a transformer with dots in the reverse direction, and capital M is the mutual inductance, it is given as 1 Henry. Then you have 8 ohms, and the mesh currents are indicated as I1t and I2t. It is given that Et is equal to 6 ut, which means that capital E of s is equal to 6 divided by s, all right, and that prior to the switching action, all initial energy was 0, and capital M equal to 1 Henry, you are required to find out I1t and I2t. All right. This is an exercise in which the standard convention, where capital M is considered positive, has been done away with. The dots have been reversed. So, M should have been negative, but you notice that the current has also been reversed, and therefore, we go back to our original equations. 2 negatives make 1 positive. Is that clear? The current has also been reversed, and therefore, my equations I can write down now by inspection the equations for the two meshes. 6 by S would be 3 plus, well, L1 and L2 are given, this is 1 Henry and this is 2 Henry. So it would be 3 plus S multiplied by I1 plus, it will be a plus sign, the mutual inductance is 1, so its impedance is Sm equal to S times I2. The plus sign has been restored because dots have been reversed, current has also been reversed. Okay. And the other equation would be 0. In the secondary, obviously there is no source, therefore 0 would be equal to SI1 plus 8 plus 2S multiplied by I2. And now the problem is to find I1 and I2. Obviously this is a simple problem. 3 plus S, 8 plus 2S, S, and in the numerator the first column replaced by the right hand side or the left hand side here, 6 by S 0, S, 8 plus 2S, and now you can make simplifications. My simplification gives me the result I1 equal to, once again a pinch of salt is to be added, S plus 4 divided by S squared plus 20S plus 48. Unfortunately I couldn't factorize this because I don't know, no factors of 48, no two factors of 48 add up to 20. 8 plus 6 is 14, 4 plus 12 is 16.
So the equation is S square plus 14 plus
14S
24.
plus 24.
S square plus 14 plus 24.
Yeah.
Oh, I see, I had made a mistake then.
And the solution is
Minus 2.
Just a minute, let me check. 3 plus S, 8 plus 2S minus S squared. So 20, oh yes, I made a mess. This is 24, this is 24 and this is 14. Now 12 and 2, oh wonderful. Therefore I1 equal to 12 by S, S plus 4. Is the numerator all right?
Yes.
Okay. So it becomes S plus 2, S plus 12, and obviously this will be the sum of 3 terms. There will be a 1 by S term, 1 by S plus 2, 1 by S plus 12, and you can find out I1t by inversion. Similarly then you find I2t. Alright, I have time for just one more problem and I will take 7-11. At the bottom of this line, it has not come out well in my, find I2t using Thevenin's theorem. Find I2t using Thevenin's theorem. The excitation is E of t equal to 100 cosine 20t, that t is missing, then multiplied by ut. Assume 0 initial energy. The circuit is this E, then you have 10 ohms and 2 Henry, then 30 ohms and 6 Henry, then you have 7.5 ohm, and this is the current that you have to find out, I2. And you have to apply Thevenin's theorem. Obviously Thevenin's theorem means this is the load now. So you will have to apply Thevenin's theorem to the left of this line. And what is E of S? Is 100 multiplied by S divided by S squared plus 400. Wonderful. We know E of S, therefore Vt, the Thevenin voltage, would be 100 S. I solved this by inspection. S squared plus 400 multiplied by Vt means this is open, and therefore 30 plus 6S divided by, what do we get, 40 plus 8s. Well, don't you see that they cancel out? S plus 5 cancels out, so it becomes simply 6 by 8, which is 3 by 4, 100s divided by s squared plus 400. Okay? This is a case of degeneracy. Normally, I should have a cubic polynomial in the denominator. It's a quadratic because there is a cancellation of terms. Okay, so Vt equals to 75s divided by s squared plus 400. And what is Zt? Zt is the parallel combination of 30 plus 6s, 10 plus 2s divided by 40 plus 8s. And once again you see that there is a cancellation. Okay, I get 3 by 4 multiplied by 2 s plus 5. Agreed? This is equal to 3 by 2 s plus 5 Zt. All right. Why does this happen? Because the time constant of this circuit is the same as the time constant of this circuit. Okay, so the two combine to give you a simple RL circuit. Is that clear? The ratio of R by L here is the same as the ratio of R by L here. The time constants are the same. Okay, and therefore I sub 2 is equal to Vt divided by Zt plus the current in this Zt plus 7.5. Is this point clear? Our Thevenin's theorem says that we have Vt, then series Zt and this 7.5. The current therefore is Vt by Zt plus 7.5, and you can notice that here also there is a simplification. 3 by 2 multiplied by 5 is 15 by 2, which is 7.5. So the denominator here shall be simply 3 by 2 s plus 10. That is correct. And whatever the numerator is, you can now go ahead and solve it. Okay. You go ahead and do it. Okay. This is where we close.